In an isosceles triangle, the two sides of equal length are legs, and the third side is the base. See Figure 3.22. The point at which the two legs meet is the vertex of the triangle, and the angle formed by the legs and opposite the base is the vertex angle. The two remaining angles are base angles. If segment AC is congruent to segment BC in the figure below, then triangle ABC is isosceles with legs segment AC and segment BC, base AB, vertex angle C, and base angles at A and B. When segment AC is congruent to BC, we see that the base, segment AB, of this isosceles triangle is not necessarily the bottom side. Consider triangle ABC in Figure 3.23a. Each angle of a triangle has a unique angle bisector, and this may be indicated by a ray or segment from the vertex of the bisected angle. The angle bisector creates two congruent angles. In Figure 3.23a, angle 1 is congruent to angle 2. Just as an angle bisector begins at the vertex of an angle, the median also joins a vertex to the midpoint of the opposite side. Generally, the median from a vertex of a triangle is not the same as the angle bisector from that angle. In Figure 3.23b, angle BAM and angle MAC are not congruent angles. An altitude is a line segment drawn from a vertex to the opposite side such that it is perpendicular to the opposite side. In Figure 3.23c, segment AE is the altitude of triangle BAC. Finally, the perpendicular bisector of a side of a triangle is shown as a line in Figure 3.23d. A segment or ray could also perpendicularly bisect a side of the triangle. In Figure 3.24, segment AD is the bisector of angle BAC. Segment AE is the altitude from point A to segment BC. Point M is the midpoint of segment BC. Segment AM is the median from point A to segment BC. And line FM is the perpendicular bisector of segment BC. An altitude can actually lie in the exterior of a triangle. In Figure 3.25, obtuse triangle, triangle RST, the altitude from point R must be drawn to an extension of side segment ST. Later we will use the length h of the altitude RH and the length b of side ST in the following formula for the area of a triangle. Area equals 1/2 base times height. Any angle bisector and any median necessarily lie in the interior of the triangle. Each triangle has three altitudes, one from each vertex, as these are shown for triangle ABC in Figure 3.26. The three altitudes seem to meet at a common point. Theorem 3.1.1. Corresponding altitudes of congruent triangles are congruent. Each triangle has three medians, one from each vertex to the midpoint of the opposite side. As the medians are drawn for triangle DEF in Figure 3.28a, it appears that the three medians intersect at a point. Each triangle has three angle bisectors, one for each of the three angles. As these are shown for triangle MNP in Figure 3.28b, it appears that the three angle bisectors have a point in common. Each triangle has three perpendicular bisectors for its sides. These are shown for triangle RST in Figure 3.28c. Like the altitudes, medians, and angle bisectors, the perpendicular bisectors of the sides also meet at a single point. The angle bisectors, like the medians, of a triangle always meet in the interior of the triangle. However, the altitudes, like the perpendicular bisectors of the sides, can meet in the exterior of the triangle. See Figure 3.28c. In Figure 3.29, the bisector of the vertex angle of isosceles triangle ABC is a line segment of symmetry for triangle ABC. Theorem 3.3.2. The bisector of the vertex angle of an isosceles triangle separates the triangle into two congruent triangles. Give a formal proof of Theorem 3.3.2. Theorem 3.3.2. The bisector of the vertex angle of an isosceles triangle separates the triangle into two congruent triangles. Given Isosceles triangle ABC with segment AB congruent to segment BC. Ray BD bisects angle ABC. See figure 3.29. Prove triangle ABD is congruent to triangle CBD. Proof. Statements. Reasons. Statement 1. Isosceles triangle ABC with segment AB congruent to segment BC. Reason 1. Given. Statement 2. Ray BD bisects angle ABC. Reason 2. Given. Statement 3. Angle 1 is congruent to angle 2. Reason for 3. The bisector of an angle separates it into two congruent angles. 4. Segment BD is congruent to segment BD. Reason for 4. Identity. Statement 5. Triangle ABD is congruent to triangle CBD. Reason 5. Side angle side. Consider figure 3.30 and the following three descriptions, which are coded D for determined, U for underdetermined, and O for overdetermined. D. Draw a line segment from A perpendicular to segment BC so that the terminal point is on segment BC. Determined because the line from A perpendicular to BC is unique. See figure 3.30a. U. Draw a line segment from A to segment BC so that the terminal point is on segment BC. Underdetermined because many line segments are possible. See figure 3.30b. O. Draw a line segment from A perpendicular to segment BC so that it bisects segment BC. Overdetermined because the line segment from A drawn perpendicular to BC will not contain the midpoint M of BC. See figure 3.30c. Theorem 3.3.3. If two sides of a triangle are congruent, then the angles opposite these sides are also congruent. In some instances, a carpenter may want to get a quick, accurate measurement without having to go to his or her tools. Suppose that the carpenter's square shown in figure 3.33 is handy, but that a miter box is not nearby. If two marks are made at lengths of 4 inches from the corner of the square, and these are then joined, what size angle is determined? You should see that each angle indicated by an arc measures 45 degrees. Theorem 3.3.4. If two angles of a triangle are congruent, then the sides opposite these angles are also congruent. When all three sides of a triangle are congruent, the triangle is equilateral. If all three angles are congruent, then the triangle is equiangular. Corollary 3.3.5. An equilateral triangle is also equiangular. Corollary 3.3.6. An equiangular triangle is also equilateral. An equilateral or equiangular triangle has line symmetry with respect to each of the three axes shown in figure 3.35. Definition. The perimeter of a triangle is the sum of the lengths of its sides. Thus, if A, B, and C are the lengths of the three sides, then the perimeter P is given by P equals A plus B plus C. See figure 3.36. Many of the properties of triangles that we have studied earlier are summarized in table 3.1.